In this video, we're going to take a look at another technique that we have for integration called trig substitution. So this is going to give us a way to find the integral of functions like x cubed times the square root of 9 minus x squared. And we're basically going to use this technique anytime we've got, or many times when we have a square root like this where it's the square root of a squared minus x squared, or if we have the square root of a squared plus x squared, or if we have the square root of x squared minus a squared. So kind of all the variations, because this one, if we flip-flop them, one in the middle there, it's the same thing. So, all the variations of two perfect squares being added or subtracted underneath the square root. So we're going to look at a technique where we use substitution kind of a novel way with trig functions. So let's set this up with this problem here. We're going to have a triangle here, and we're going to label one of our angles theta. And what we're going to do on this triangle is take these values that are underneath our square root. So we've got 9, which is going to be 3 squared, and x squared, which is x being squared. Maybe we'll write it like that so we can kind of see how those two are related. And we're going to make x be the opposite side and 3 the hypotenuse. So our adjacent side here, how we can figure that out, remember with a right triangle, this is a right triangle, that the Pythagorean theorem is true. So we've got x squared plus that adjacent side squared is equal to our hypotenuse squared. So the adjacent side is 9 minus x squared underneath the square root. If we subtract x squared from both sides and then take the square root. So our adjacent side is exactly the square root that we have inside of our integral, that square root right there. So what we're going to be able to do is to replace that with a trig function, because things that we know that are true about this triangle that we created here, and again, we created it, so we know that sine of that angle theta is x over 3. We could rewrite that as 3 times sine of theta is equal to x. We also could say that cosine of theta is equal to that square root of 9 minus x squared divided by 3, or that 3 times cosine of theta is equal to the square root of 9 minus x squared. So now if we kind of look at these two statements that we have right here, our 3 sine of theta is equal to x, and our 3 cosine of theta is equal to the square root of 9 minus x squared, and we take our integral that we started with, so the integral of x cubed times 9x squared dx. So this x to the third power that we've got sitting there in the first term, we can replace that with 3 sine of theta being cubed. So we're using this substitution right here, that x is equal to 3 sine of theta. And then we're going to do the same thing with this substitution right here. So that square root, we can replace that with 3 cosine of theta. Now we do have a bit of a problem because we didn't take care of this dx that's sitting right here. It's still sitting there. And that's a problem. We need our variables to be all the same in our integral. So we are changing our variable to theta. So we need to make sure that we change our dx to a d theta. So how we can do that is if we take this relationship, our 3 sine of theta is equal to x, and we differentiate both sides. We get 3 cosine of theta, and then this is dx d theta. The variable that we're differentiating with respect to is theta, and we can multiply both sides by theta and get that 3 cosine of x d theta is equal to dx. Now, usually it's about at this point where a student asks me, hey, why don't we set up the triangle where the adjacent side is x and the hypotenuse is 3, so then this side is 9x squared, or 9 minus x squared underneath our square root. You absolutely 100% could do this problem set up that way. The reason why we don't is actually this part right here, where we're converting that dx to a d theta, because when we take the derivative, well, because this would have us, with cosine of theta is equal to x over 3. So we would be doing this process that we just did right here, that I'll circle again in green. We would be doing that with cosine, and we'd end up with our derivative being negative sine. So doing this setup the way we did in pink versus how we set it up in green, it keeps our signs positive more, in the longer term. So that's really the reason. It's as simple as that. You could totally set this up the other way. It does not have to be set up the way that I set it up. So back to our integral, we get 3 cubed sine cubed times 3 cosine of theta, and then our dx right here, we just learned that dx is 3 times cosine of x d theta. So we can replace that with 3 cosine of theta d theta. So I'll underline that in green there, just to make sure we can, again, realize where we got that from. So now where we're sitting here, boy, we've got an awful lot of 3's in this. So we could take all of those out in front. There are 5 of them. Right, let's grab a different color here. We got 3 to the 3rd, and then another 3, and then another 3. So we have 5 of them all together. So we could figure out what 3 to the 5th is, but I'm not going to do that just now. We'll see why here in a second. It might take a minute to get why we don't want to do that just yet. But all right, now this is an integral that we've seen before, and this is one of our trig integrals. So what we can do with this is break this up as sine squared of theta times cosine squared of theta times sine of theta. So again, all I'm doing here is peeling off one of our sines from our sine cubed and putting it over by our theta, because we're going to do a substitution here in a second. We're going to replace our sine squared of theta with a 1 minus cosine squared of theta, right? Because we can do that. So we get the integral of 1 minus cosine squared of theta times cosine squared of theta times sine of theta d theta. And now we're going to do one of our regular substitutions. We're going to do u is equal to cosine of theta, so du is equal to negative sine of theta d theta. We'll move that negative over with the du. And see, this is why it's kind of annoying to have cosine being what we're doing with our substitution. That's why up above we used sine. So now in our integral, that 3 to the 5th still out front, we're going to have the integral of 1 minus u squared times negative 1, and then du. So we had to do a second substitution on this, and sometimes we do have to do that on these. So we'll get 3 to the 5th, and then doing our multiplication here and multiplying by the negative 1, we're going to get negative u squared plus u to the 4th du. And this we can take the integral of, so we get 3 to the 5th. And maybe we'll write this just in a slightly different order. All right, so we get 1/5 u to the 5th minus 1/3 u to the 3rd. All right, now we have to substitute back. Remember, our variable was not u. Our variable originally was x. And man, we've done 2 types of substitution, so we're going to have to substitute back twice. So first off, this u is cosine of theta. So let's start there. So we get 3 to the 5th, and then 1/5 cosine of theta to the 5th. I'm going to kind of write it slightly different than we normally do. Cosine of theta cubed plus c. Now, cosine of theta, way back up here, cosine of theta is that. It is the square root of 9 minus x squared over 3. And it's that because that's how we set it up. We set up this triangle, we made our sides x and 3 and the square root of 9 minus x squared. So I'm going to take this and copy this and paste it down here for us, just so we remember that that's what we need to put back into our integral. We need to replace this cosine of theta that we have in both of those places with the square root of 9 minus x squared over 3. So we're still going to have that 3 to the 5th out in front there. And then we have 1/5, and we're going to have, let's see, the square root of 9 minus x squared over 3 to the 5th minus 1/3. square root of 9 minus x squared over 3 cubed plus c. So technically we have it right here. This is our integral. This is our answer. There is some things that we can do to, make this a little bit nicer, and it's mostly in particular with our coefficients, because we could rewrite this as 9 minus x squared to the 5/2 over 3 to the 5th power. So again, we're just giving that exponent to both of the top and the bottom of our fraction there. And then if we multiply that 3 to the 5th through, so we get 3 to the 5th times 1/5 times 9 squared. So we're just writing this again, just to simplify things. And we'll see we do get a fairly simple answer when we're done here. Sorry, I'm trying to write too fast. There we go, 3 cubed plus c. Okay, so what cancels? Well, we have 3 to the 5th on the top there, 3 to the 5th on the bottom there. Over here, we've got 1 plus 3 more, so we had all but one of those cancel, because we have 4 on the bottom in that second term and 5 on the top. So what do we end up with? We end up with 9 minus x squared to the 5/2 over just this 5, and then minus 3 times 9 minus x squared to the 3 over 2 plus c, and there is our answer.